sub-projects, most of which are focused on data persistence with a variety of different database types. A few of the most popular Spring Data projects include these. Spring Data JDBC, JDBC persistence against a relational database. Spring Data JPA, JPA persistence against a relational database. Spring Data MongoDB, persistence to a Mongo document database. Spring Data Neo4j, persistence to a Neo4j graph database. Spring Data Redis, persistence to a Redis key-value store. Spring Data Cassandra, persistence to a Cassandra column store database. One of the most interesting and useful features provided by Spring Data for all of these projects is the ability to automatically create repositories based on a repository specification interface. Consequently, persistence with Spring Data projects has little or no persistence logic and involves writing only one or more repository interfaces. Let's see how to apply Spring Data JDBC to our project to simplify data persistence with JDBC. First, you'll need to add Spring Data JDBC to the project build. Section 3.2.1, Adding Spring Data JDBC to the build. Spring Data JDBC is available as a starter dependency for Spring Boot apps. When added to the project's pom.xml file, the starter dependency looks like the following code snippet. You will no longer need the JDBC starter that gave us JDBC template, so you can remove the starter that looks like this. You'll still need a database, however, so don't remove the H2 dependency. Section 3.2.2, Defining Repository Interfaces. Fortunately, we've already created ingredient repository and order repository, so much of the work in defining our repositories is already done. But we'll need to make a subtle change to them in order to use them with Spring Data JDBC. Spring Data will automatically generate implementations for our repository interfaces at runtime, but it will do that only for interfaces that extend one of the repository interfaces provided by Spring Data. At the very least, our repository interfaces will need to extend repository so that Spring Data knows to create the implementation automatically. For example, here's how you might write ingredient repository such that it extends repository. As you can see, the repository interface is parameterized. The first parameter is the type of the object to be persisted by this repository, in this case, ingredient. The second parameter is the type of the persisted object's ID field. For ingredient, that's string. Although ingredient repository will work as shown here by extending repository, Spring Data also offers CRUD repository as a base interface for common operations, including the 3 methods we've defined in ingredient repository. So instead of extending repository, it's often easier to extend CRUD repository, as shown next. Similarly, our order repository can extend CRUD repository as shown in the next listing. In both cases, because CRUD repository already defines the methods you need, there's no need to explicitly define them in the ingredient repository and order repository interfaces. And now you have your 2 repositories. You might be thinking that you need to write the implementations for both repositories, including the dozen methods defined in CRUD repository. But that's the good news about Spring Data. There's no need to write an implementation. When the application starts, Spring Data automatically generates an implementation on the fly. This means the repositories are ready to use from the get-go. Just inject them into the controllers and you're done. What's more, because Spring Data automatically creates implementations of these interfaces at runtime, you no longer need the explicit implementations in JDBC ingredient repository and JDBC order repository. You can delete those 2 classes and never look back. Section 3.2.3, Annotating the domain for persistence. The only other thing we'll need to do is annotate our domain classes so that Spring Data JDBC will know how to persist them. Generally speaking, this means annotating the identity properties with @ID so that Spring Data will know which field represents the object's identity, and optionally annotating the class with @table. For example, the taco order class might be annotated with @table and @id as shown in the following code. The @table annotation is completely optional. By default, the object is mapped to a table based on the domain class name. In this case, taco order is mapped to a table named taco_order. If that's fine for you, then you can leave the @table annotation off completely or use it without parameters. But if you'd prefer to map it to a different table name, then you can specify the table name as a parameter to @table like this. As shown here, taco order will be mapped to a table named taco_cloud_order. As for the @id annotation, it designates the ID property as being the identity for a taco order. All other properties in taco order will be mapped automatically to columns based on their property names. For example, the delivery name property will be automatically mapped to the column named delivery_name. But if you want to explicitly define the column name mapping, you could annotate the property with @column like this. In this case, @column is specifying that the delivery name property will be mapped to the column whose name is customer_name. You'll also need to apply @table and @id to the other domain classes. This includes @ingredient and taco. As for ingredient ref, it will be mapped automatically to the table whose name is ingredient_ref, which is perfect for our application. You can annotate it with @table if you want, but it's not necessary. And the ingredient_ref table has no identity column, so there is no need to annotate anything in ingredient ref with @id. With these small changes, not to mention the complete removal of the JDBC ingredient repository and JDBC order repository classes, you now have a lot less persistence code. Even so, the repository implementations that are generated at runtime by Spring Data still do everything that the repositories using JDBC template did. In fact, they have potential for doing even more, because the two repository interfaces extend CRUD repository, which offers a dozen or so operations for creating, reading, updating, and deleting objects. Section 3.2.4 Preloading data with command line runner. When working with JDBC template, we preloaded the ingredient data at application startup using data.sql, which was executed against the database when the data source bean was created. That same approach will work with Spring Data JDBC. In fact, it will work with any persistence mechanism for which the backing database is a relational database. But let's see another way of populating a database at startup that offers a bit more flexibility. Spring Boot offers two useful interfaces for executing logic when an application starts up: Command Line Runner and Application Runner. These two interfaces are quite similar. Both are functional interfaces that require that a single run method be implemented. When the application starts up, any beans in the application context that implement Command Line Runner or Application Runner will have their run methods invoked after the application context and all beans are wired up, but before anything else happens. This provides a convenient place for data to be loaded into the database. Because both Command Line Runner and Application Runner are functional interfaces, they can easily be declared as beans in a configuration class using a @beanAnnotated method that returns a lambda function. For example, here's how you might create a data loading Command Line Runner bean. Here, the ingredient repository is injected into the bean method and used within the lambda to create ingredient objects. The run method of Command Line Runner accepts a single parameter that is a string vararg containing all of the command line arguments for the running application. We don't need those to load ingredients into the database, so the args parameter is ignored. Alternatively, we could have defined the data loader bean as a lambda implementation of Application Runner like this. The key difference between Command Line Runner and Application Runner is in the parameter passed to the respective run methods. Command Line Runner accepts a string vararg, which is a raw representation of arguments passed on the command line. But Application Runner accepts an application arguments parameter that offers methods for accessing the arguments as parsed components of the command line. For example, suppose that we want our application to accept a command line with arguments such as --version 1.2.3 and need to consider that argument in our loader bean. If using a command line runner, we'd need to search the array for -version and then take the very next value from the array. But with Application Runner, we can query the given application arguments for the -version argument like this. The getOptionValues method returns a list string to allow for the option argument to be specified multiple times. In the case of either Command Line Runner or Application Runner, however, we don't need command line arguments to load data. So the args parameter is ignored in our data loader bean. What's nice about using Command Line Runner or Application Runner to do an initial data load is that they are using the repositories to create the persisted objects instead of a SQL script. This means that they'll work equally well for relational databases and non-relational databases. This will come in handy in the next chapter when we see how to use Spring Data to persist to non-relational databases. But before we do that, let's have a look at another Spring Data project for persisting data in relational databases. Spring Data JPA. Section 3.3. Persisting Data with Spring Data JPA. Whereas Spring Data JDBC makes easy work of persisting data, the Java Persistence API, JPA, is another popular option for working with data in a relational database. Spring Data JPA offers an approach to persistence with JPA similar to what Spring Data JDBC gave us for JDBC. To see how Spring Data works, you're going to start over, replacing the JDBC-based repositories from earlier in this chapter with repositories created by Spring Data JPA. But first, you need to add Spring Data JPA to the project build. Section 3.3.1. Adding Spring Data JPA to the project. Spring Data JPA is available to Spring Boot applications with the JPA starter. This starter dependency not only brings in Spring Data JPA, but also transitively includes Hibernate as the JPA implementation, as shown here. If you want to use a different JPA implementation, then you'll need to at least exclude the Hibernate dependency and include the JPA library of your choice. For example, to use Eclipse Link instead of Hibernate, you'll need to alter the build as follows. Note that there may be other changes required, depending on your choice of JPA implementation. Consult the documentation of your chosen JPA implementation for details. Now let's revisit your domain objects and annotate them for JPA persistence. Section 3.3.2. Annotating the domain as entities. As you've already seen with Spring Data JDBC, Spring Data does some amazing things when it comes to creating repositories. But unfortunately, it doesn't help much when it comes to annotating your domain objects with JPA mapping annotations. You'll need to open up the ingredient, taco, and taco order classes and throw in a few annotations. First up is the ingredient class, shown next. To declare this as a JPA entity, ingredient must be annotated with @entity. And its ID property must be annotated with @ID to designate it as the property that will uniquely identify the entity in the database. Note that this @ID annotation is the JPA variety from the jvax.persistence package, as opposed to the @ID provided by Spring Data in the org.springframework.data.annotation package. Also note that we no longer need the @table annotation or need to implement persistable. Although we could still use @table here, it is unnecessary when working with JPA and defaults to the name of the class, ingredient in this case. As for persistable, it was only necessary with Spring Data JDBC to determine whether or not an entity was to be created new or to update an existing entity. JPA sorts that out automatically. In addition to the JPA-specific annotations, you'll also note that you've added a @noargs constructor annotation at the class level. JPA requires that entities have a no-arguments constructor, So Lombok's @noargs constructor does that for you. You don't want to be able to use it, though, so you make it private by setting the access attribute to accessLevel.private. And because you must set final properties, you also set the force attribute to true, which results in the Lombok-generated constructor setting them to a default value of null, 0, or false, depending on the property type. You also will add an @allargs constructor to make it easy to create an ingredient object with all properties initialized. You also need a @requiredargs constructor. The @data annotation implicitly adds a required arguments constructor, but when a @noargs constructor is used, that constructor is removed. An explicit @requiredargs constructor ensures that you'll still have a required arguments constructor in addition to the private noarguments constructor. Now let's move on to the taco class and see how to annotate it as a JPA entity. As with ingredient, the taco class is now annotated with @entity and has its ID property annotated with @ID. Because you're relying on the database to automatically generate the ID value, you also annotate the ID property with @generated_value, specifying a strategy of auto. To declare the relationship between a taco and its associated ingredient list, you annotate ingredients with @many_to_many. A taco can have many ingredient objects, and an ingredient can be a part of many tacos. Finally, let's annotate the taco order object as an entity. The next listing shows the new taco order class. As you can see, the changes to taco order closely mirror the changes to taco. One significant thing worth noting is that the relationship to the list of taco objects is annotated with @one_to_many, indicating that the tacos are all specific to this one order. Moreover, the cascade attribute is set to cascadetype.all, so that if the order is deleted, the related tacos will also be deleted. Section 3.3.3 Declaring JPA repositories. When you created the JDBC template versions of the repositories, you explicitly declared the methods you wanted the repository to provide. But with Spring Data JDBC, you were able to dismiss the explicit implementation classes and instead extend the CRUD repository interface. As it turns out, CRUD repository works equally well for Spring Data JPA. For example, here's the new ingredient repository interface. In fact, the ingredient repository interface we'll use with Spring Data JPA is identical to the one we defined for use with Spring Data JDBC. The CRUD repository interface is commonly used across many of Spring Data's projects, regardless of the underlying persistence mechanism. Similarly, you can define order repository for the Spring Data JPA the same as it was for Spring Data JDBC as follows. The methods provided by CRUD repository are great for general-purpose persistence of entities. But what if you have some requirements beyond basic persistence? Let's see how to customize the repositories to perform queries unique to your domain. Section 3.3.4 Customizing repositories. Imagine that in addition to the basic CRUD operations provided by CRUD repository, you also need to fetch all the orders delivered to a given zip code. As it turns out, this can easily be addressed by adding the following method declaration to order repository. When generating the repository implementation, Spring Data examines each method in the repository interface, parses the method name, and attempts to understand the method's purpose in the context of the persisted object, a taco order in this case. In essence, Spring Data defines a sort of miniature domain-specific language, DSL, where persistence details are expressed in repository method signatures. Spring Data knows that this method is intended to find orders, because you've parameterized CRUD repository with taco order. The method name, findByDeliveryZip, makes it clear that this method should find all taco order entities by matching their delivery zip property with the value passed in as a parameter to the method. The findByDeliveryZip method is simple enough, but Spring Data can handle even more interesting method names as well. Repository methods are composed of a verb, an optional subject, the word by, and a predicate. In the case of find by delivery zip, the verb is find and the predicate is delivery zip. The subject isn't specified and is implied to be a taco order. Let's consider another more complex example. Suppose that you need to query for all orders delivered to a given zip code within a given date range. In that case, the following method, when added to order repository, might prove useful. Figure 3.2 illustrates how Spring Data parses and understands the read orders by delivery zip and placed at between method when generating the repository implementation. As you can see, the verb in read orders by delivery zip and placed at between is read. Spring Data also understands find, read, and get as synonymous for fetching one or more entities. Alternatively, you can also use count as the verb if you want the method to return only an int with the count of matching entities. Although the subject of the method is optional, here it says orders. Spring Data ignores most words in a subject, so you could name the method read puppies by, and it would still find taco order entities, because that is the type that CRUD repository is parameterized with. The predicate follows the word by in the method name and is the most interesting part of the method signature. In this case, the predicate refers to two taco order properties, delivery zip and placed at. The delivery zip property must be equal to the value passed into the first parameter of the method. The keyword between indicates that the value of delivery zip must fall between the values passed into the last two parameters of the method. In addition to an implicit equals operation and the between operation, Spring Data method signatures can also include any of the following operators. Is after, is greater than, is greater than equal, is before, is less than, is less than equal, is between, is null, is not null, is in, is not in, is starting with, starts with, is ending with, ends with, is containing, contains, is like, is not like, is true, is false, is equals, is not, ignoring case, ignores case. As alternatives for ignoring case and ignores case, you can place either all ignoring case or all ignores case on the method to ignore case for all string comparisons. For example, consider the following method. Finally, you can also place order by at the end of the method name to sort the results by a specified column. For example, to order by the delivery to property, use the following code. Although the naming convention can be useful for relatively simple queries, it doesn't take much imagination to see that method names could get out of hand for more complex queries. In that case, feel free to name the method anything you want and annotate it with a @query to explicitly specify the query to be performed when the method is called, as this example shows. In this simple usage of @query, you ask for all orders delivered in Seattle. But you can use @query to perform virtually any JPA query you can dream up, even when it's difficult or impossible to achieve the query by following the naming convention. Custom query methods also work with Spring Data JDBC, but with the following key differences. All custom query methods require @query. This is because, unlike JPA, there's no mapping metadata to help Spring Data JDBC automatically infer the query from the method name. All queries specified in @query must be SQL queries, not JPA queries. In the next chapter, we'll expand our use of Spring Data to work with non-relational databases. When we do, you'll see that custom query methods work very similarly, although the query language used in @query will be specific to the underlying database. Summary. Spring's JDBC template greatly simplifies working with JDBC. Prepared Statement Creator and Key Holder can be used together when you need to know the value of a database-generated ID. Spring Data JDBC and Spring Data JPA make working with relational data as easy as writing a repository interface. Chapter 4. Working with Non-Relational Data. This chapter covers persisting data to Cassandra, data modeling in Cassandra, working with document data in MongoDB. They say that variety is the spice of life. You probably have a favorite flavor of ice cream. It's that one flavor that you choose the most often because it satisfies that creamy craving more than any other. But most people, despite having a favorite flavor, try different flavors from time to mix things up. Databases are like ice cream. For decades, the relational database has been the favorite flavor for storing data. But these days, we have more options available than ever before. So-called NoSQL databases, see this link, offer different concepts and structures in which data can be stored. And although the choice may still be somewhat based on taste, some databases are better suited for persisting different kinds of data than others. Fortunately, Spring Data has you covered for many of the NoSQL databases, including MongoDB, Cassandra, Couchbase, Neo4j, Redis, and many more. And fortunately, the programming model is nearly identical, regardless of which database you choose. There's not enough space in this chapter to cover all of the databases that Spring Data supports, but to give you a sample of Spring Data's other flavors, we'll look at two popular NoSQL databases, Cassandra and MongoDB, and see how to create repositories to persist data to them. Let's start by looking at how to create Cassandra repositories with Spring Data. Section 4.1. Working with Cassandra repositories. Cassandra is a distributed, high-performance, always available, eventually consistent, partitioned column store NoSQL database. That's a mouthful of adjectives to describe a database, but each one accurately speaks to the power of working with Cassandra. To put it in simpler terms, Cassandra deals in rows of data written to tables, which are partitioned across one to many distributed nodes. No single node carries all the data, but any given row may be replicated across multiple nodes, thus eliminating any single point of failure. Spring Data Cassandra provides automatic repository support for the Cassandra database that's quite similar to, and yet quite different from, what's offered by Spring Data JPA for relational databases. In addition, Spring Data Cassandra offers annotations for mapping application domain types to the backing database structures. Before we explore Cassandra any further, it's important to understand that although Cassandra shares many concepts similar to relational databases like Oracle and SQL Server, Cassandra isn't a relational database and is in many ways quite a different beast. I'll explain the idiosyncrasies of Cassandra as they pertain to working with Spring Data, but I encourage you to read Cassandra's own documentation, at this link, for a thorough understanding of what makes it tick. Let's get started by enabling Spring Data Cassandra in the Taco Cloud project. Section 4.1.1. Enabling Spring Data Cassandra. To get started using Spring Data Cassandra, you'll need to add the Spring Boot Starter dependency for non-reactive Spring Data Cassandra. There are actually two separate Spring Data Cassandra starter dependencies to choose from, one for reactive data persistence and one for standard non-reactive persistence. We'll talk more about writing reactive repositories later in Chapter 15. For now, though, we'll use the non-reactive starter in our build as shown here. This dependency is also available from the initializer by checking the Cassandra checkbox. It's important to understand that this dependency is in lieu of the Spring Data JPA starter or Spring Data JDBC dependencies we used in the previous chapter. Instead of persisting Taco Cloud data to a relational database with JPA or JDBC, you'll be using Spring Data to persist data to a Cassandra database. Therefore, you'll want to remove the Spring Data JPA or Spring Data JDBC starter dependencies and any relational database dependencies, such as JDBC drivers or the H2 dependency, from the build. The Spring Data Cassandra starter dependency brings a handful of dependencies to the project, specifically the Spring Data Cassandra library. As a result of Spring Data Cassandra being in the runtime class path, auto-configuration for creating Cassandra repositories is triggered. This means you're able to begin writing Cassandra repositories with minimal explicit configuration. Cassandra operates as a cluster of nodes that together act as a complete database system. If you don't already have a Cassandra cluster to work with, you can start a single node cluster for development purposes using Docker, like this. This starts the single node cluster and exposes the node's port, 9042, on the host machine so that your application can access it. You'll need to provide a small amount of configuration, though. At the very least, you'll need to configure the name of a key space within which your repositories will operate. To do that, you'll first need to create such a key space. Note: in Cassandra, a key space is a grouping of tables in a Cassandra node. It's roughly analogous to how tables, views, and constraints are grouped in a relational database. Although it's possible to configure Spring Data Cassandra to create the key space automatically, it's typically much easier to manually create it yourself, or to use an existing key space. Using the Cassandra CQL, Cassandra Query Language shell, you can create a key space for the Taco Cloud application. You can start the CQL shell using Docker, like this. Note: if this command fails to start up the CQL shell with an error indicating unable to connect to any servers, wait a minute or two and try again. You need to be sure that the Cassandra cluster is fully started before the CQL shell can connect to it. When the shell is ready, use the create keyspace command like this. Put simply, this will create a key space named Taco Cloud with simple replication and durable writes. By setting the replication factor to 1, you ask Cassandra to keep one copy of each row. The replication strategy determines how replication is handled. The simple strategy replication strategy is fine for single data center use and for demo code, but you might consider the network topology strategy if you have your Cassandra cluster spread across multiple data centers. I refer you to the Cassandra documentation for more details of how replication strategies work and alternative ways of creating key spaces. Now that you've created a key space, you need to configure the spring.data.cassandra.keyspace-name property to tell Spring Data Cassandra to use that key space, as shown next. Here, you also set the spring.data.cassandra.schema-action to recreate. This setting is very useful for development purposes because it ensures that any tables and user-defined types will be dropped and recreated every time the application starts. The default value, none, takes no action against the schema and is useful in production settings where you'd rather not drop all tables whenever an application starts up. Finally, the spring.data.cassandra.local-datacenter property identifies the name of the local data center for purposes of setting Cassandra's load balancing policy. In a single node setup, Data Center 1 is the value to use. For more information on Cassandra load balancing policies and how to set the local data center, see the DataStax Cassandra drivers reference document at this link. These are the only properties you'll need for working with a locally running Cassandra database. In addition to these two properties, however, you may wish to set others, depending on how you've configured your Cassandra cluster. By default, Spring Data Cassandra assumes that Cassandra is running locally and listening on port 9042. If that's not the case, as in a production setting, you may want to set the spring.data.cassandra.contact-points and spring.data.cassandra.port properties as follows. Notice that the spring.data